September 6, 1976. Hakodate Airport, northern Japan. A diplomatic crisis was unfolding in real time. American intelligence officers, Japanese defense officials, and Soviet diplomats all converged on this small civilian airport in the northernmost reaches of Japan. Inside a hastily secured hangar surrounded by armed guards and security cordons sat the prize that would change everything we thought we knew about Soviet military aviation. A MiG-25 Foxbat, intact, its system still warm from the flight that had brought it across 200 miles of open ocean from Soviet territory. The pilot, Senior Lieutenant Viktor Belenko, was already in American custody, requesting asylum. His aircraft, the Soviet Union's most feared interceptor, the machine that had terrified Western military planners for nearly a decade, now sat under foreign examination for the first time in its operational history. American intelligence had waited years for this moment. Every intelligence agency in the West had MiG-25 acquisition as a top priority. CIA operations had tried to recruit Soviet pilots. The NSA had intercepted communications about the aircraft. Reconnaissance satellites had photographed it on runways and in flight. But nothing compared to having the actual machine, something that could be touched, measured, weighed, tested, dissected down to every rivet and wire, every weld and component. What they would discover in the following weeks of intensive examination would fundamentally change how military engineers understood the relationship between technological sophistication and actual operational effectiveness. The initial reports that filtered back to Washington and Langley reflected confusion and dismissiveness. CIA engineers began calling it the Steel Pig, a nickname that spread quickly through the intelligence community. They were laughing at what seemed like crude, heavy, outdated Soviet engineering. Steel construction in a supersonic aircraft, vacuum tubes instead of transistors, welds that looked like they came from a World War II shipyard. This was the superweapon that had shaped a decade of American defense policy. But as the analysis continued, as engineers dug deeper into the aircraft's construction and began to understand not just what it was, but why it was built that way, that mockery turned to grudging respect, then to something approaching awe. This wasn't primitive technology. This was brilliance disguised as simplicity. This was engineering genius operating under constraints that Western designers had never faced. To understand why the MiG-25's arrival in Japan sent shockwaves through Western intelligence communities worldwide, why this single aircraft defection became one of the most significant intelligence coups of the entire Cold War era, we need to go back to the early 1960s and examine the strategic environment that gave birth to this extraordinary machine. The United States had just unveiled the XB-70 Valkyrie, a massive six-engine strategic bomber designed to penetrate Soviet airspace at Mach 3 and 70,000 feet altitude. The Valkyrie represented American aerospace engineering at its absolute zenith. It would fly so high and so fast that theoretically no Soviet interceptor could touch it. Soviet surface-to-air missiles of the early 1960s couldn't reach that altitude. Soviet fighters couldn't sustain those speeds. The strategic implications were profound and terrifying for Soviet military planners. At the same time, Lockheed was developing the SR-71 Blackbird, an aircraft that promised speeds exceeding Mach 3.2 and operational altitudes above 85,000 feet. The Blackbird would be able to photograph the entire Soviet Union with impunity, mapping every military installation, tracking every troop movement, monitoring every strategic asset. Soviet military planners recognized that they faced an existential problem of unprecedented scope. Their entire air defense network, billions of rubles invested in radar stations, missile sites, and interceptor bases, was fundamentally built around stopping subsonic bombers flying at medium altitudes. The American B-52s, the primary threat throughout the 1950s, cruised at around 500 miles per hour at 40,000 feet. Soviet defenses were optimized for exactly that threat profile. The Americans deployed hypersonic platforms like the XB-70 in significant numbers. If reconnaissance aircraft like the SR-71 could overfly Soviet territory at will, Soviet airspace would become essentially transparent. The entire concept of strategic depth, so crucial to Soviet military doctrine after the devastating losses of World War II, would become meaningless. American bombers could strike deep into Soviet territory with minimal warning time. American reconnaissance could monitor Soviet military readiness continuously. The strategic balance would tilt decisively in favor of the United States. The Soviet response came from the Mikoyan-Gurevich Design Bureau, one of the premier aircraft manufacturers in the Soviet Union. The design team was led by Mikhail Gurevich, though Artem Mikoyan had already passed away by this point. Were given a seemingly impossible task. Design an interceptor capable of catching and destroying aircraft flying at Mach 3 or above, at altitudes over 70,000 feet. No existing fighter could do this. The physics seemed to prohibit it. But Soviet engineers approached the problem methodically, accepting certain limitations in order to achieve the necessary performance in the areas that mattered most. In 1964, the prototype designated the 266 took its first flight from the Gukovetsky test facility outside Moscow. Test pilots immediately recognized they were flying something unprecedented. The acceleration was brutal. Climb rate exceeded anything in Soviet or Western arsenals. By 1967, after intensive testing and refinement, the production version, designated MiG-25, entered operational service with Soviet air defense forces. The speed with which the program moved from concept to deployment was remarkable, especially compared to Western development cycles that often stretched across decades. Western intelligence knew something significant was happening at Soviet aircraft plants. Satellite imagery showed a large twin-engine aircraft with distinctive features appearing at multiple air bases. The configuration was unusual: side-mounted air intakes, twin vertical stabilizers, a wing design that suggested very high-speed optimization. Defector reports began filtering through intelligence networks. Speaking of unprecedented performance capabilities and pilots training for flight profiles unlike anything previously encountered. When the MiG-25 made its public debut at the Domodedovo Air Show near Moscow, Western observers were simultaneously impressed and alarmed. The aircraft looked menacing, powerful, purposeful. Its profile suggested raw speed and brutal effectiveness. NATO intelligence officers gave it the reporting name Foxbat, continuing the tradition of designating names for Soviet fighters. But beneath that bureaucratic label lay genuine concern. Western analysts had almost no hard technical data. They knew from radar tracking and defector reports that the MiG-25 could fly above Mach 2.8. They knew it operated at extreme altitudes that pushed the boundaries of what was considered possible for manned aircraft. Radar cross-section estimates suggested a large, powerful machine, with engines producing enormous thrust. From these fragments, American and NATO intelligence had to build a complete picture of Soviet capabilities. The problem was that Western analysts made assumptions based on what they themselves would have built to achieve such performance. To reach Mach 3 at 70,000 feet, Western engineers would use extensive titanium construction to handle the thermal loads while keeping weight manageable. They would employ advanced transistorized avionics for sophisticated fire control and radar systems. They would develop powerful but fuel-efficient engines with advanced materials and cooling systems. They would incorporate fly-by-wire flight controls with computer augmentation for stability at extreme speeds. They assumed the Soviets had done exactly the same thing, because in their minds, there was no other way. This is precisely what American designers were doing with the F-15 Eagle program, which was explicitly designed as an answer to the perceived MiG-25 threat. Initiated in the late 1960s, the F-15 represented everything American aerospace engineering could achieve. McDonnell Douglas incorporated cutting-edge technology in every system. The airframe used titanium extensively for strength and heat resistance. The avionics were transistorized and later solid-state, with sophisticated radar capable of tracking multiple targets and engaging them beyond visual range. The engines, Pratt & Whitney F100 turbofans, provided unprecedented thrust-to-weight ratio with far better fuel efficiency than previous generation engines. Flight controls were hydraulically boosted with computer augmentation for enhanced maneuverability. The F-15 cost approximately $27 million per aircraft in $1,976. The total program development cost ran into billions. But American planners considered this investment necessary to counter what they believed Soviet engineers had achieved with the MiG-25. 12 years of development, billions of dollars. The most advanced fighter ever built. And it was designed to answer a question that, as it turned out, the Soviets had solved in a way nobody in Washington expected. Then came Viktor Valerievich Belenko, a senior lieutenant in the Soviet Air Defense Force's 513th Fighter Regiment, based at Chigovka Air Base near Vladivostok. Belenko was 29 years old, married with a young son, and by all outward appearances, a model Soviet officer. He had grown up in the Soviet system, served loyally, and achieved his dream of becoming a fighter pilot. But beneath that surface loyalty, Belenko had become profoundly disillusioned with the Soviet system. He had seen the gap between propaganda and reality. He had experienced the corruption, the lies, the grinding poverty that characterized Soviet life outside the privileged circles of the Communist Party elite. He had made a decision that required extraordinary courage, would defect to the West, and he would bring his aircraft with him. The plan required perfect execution. September 6, 1976, Belenko was scheduled for a routine training flight over the Sea of Japan. The mission profile called for air combat maneuvering practice with other aircraft from his squadron. Standard procedure, nothing unusual. Belenko took off in aircraft number 31, a MiG-25 interceptor variant in standard Soviet Air Defense Forces configuration. He carried no weapons, as training flights typically flew without live missiles. He rendezvoused with the other aircraft in his flight. They began the planned exercise maneuvers. Then Belenko broke formation. He descended rapidly to low altitude, dropping below the coverage of Soviet ground radar. He turned east toward Japan. His wingman, confused by his sudden departure from the training pattern, attempted to follow and re-establish radio contact. Belenko ignored all calls. He was committed now. There was no going back. Either he would reach Japan in asylum, or he would be shot down by Soviet fighters or air defenses. Flying at near supersonic speed just above the waves, Belenko crossed 200 miles of open ocean. Soviet air defense networks detected an unidentified track heading toward Japanese airspace, but couldn't immediately identify it as one of their own aircraft. Japanese air defense systems picked up the approaching contact. They scrambled F-4 Phantom fighters from northern bases, but Belenko was already descending toward Hakodate Airport on the northern island of Hokkaido. He had chosen a civilian airport deliberately. Landing at a military base might provoke an immediate armed response. A civilian airport would create confusion, buying precious minutes to surrender to authorities before Soviet forces could react. The MiG-25 appeared in the landing pattern without warning. Air traffic controllers, stunned at seeing a Soviet military aircraft approaching their airport, tried to wave him off. Belenko ignored them. He touched down with almost no fuel remaining in his tanks. The massive aircraft, never designed for short runways or precise civilian airport approaches, hit the ground hard but stayed intact. Japanese police and airport security surrounded the aircraft immediately. Belenko emerged with his hands raised, requesting asylum. Within minutes, the Japanese government was in crisis mode. Soviet diplomats were already demanding immediate return of the aircraft and the pilot. American embassy officials were frantically trying to secure access to both. The Japanese, caught between two superpowers, tried to navigate impossible diplomatic waters. Meanwhile, intelligence teams from both countries were racing toward Hakodate. What happened next became one of the most significant intelligence examination operations of the Cold War. The Soviets demanded immediate return of the aircraft under international law. The Japanese government, technically neutral but effectively aligned with the West, stalled. They claimed the need to investigate the illegal entry into Japanese airspace. In reality, they were buying time for American intelligence to document everything about the aircraft. American and Japanese engineers worked in 12-hour shifts around the clock. They had perhaps 2 months before diplomatic pressure would force Japan to return the aircraft. Every minute counted. Every measurement, every photograph, every test could provide crucial intelligence about Soviet aerospace capabilities. The first technical teams approached the aircraft with specific expectations based on a decade of analysis and assumptions. They expected to find the cutting-edge technology that would have been necessary in Western thinking to achieve the MiG-25's known performance. What they found instead would rewrite the textbook. The first teams opened access panels in the fuselage, expecting to find titanium structure underneath. Instead, they found steel. Not exotic alloys or advanced composites, but nickel steel alloy. Heavy, relatively crude steel that would have been familiar to aircraft engineers from the 1940s. The shock was profound. Titanium had become the standard material for high-performance military aircraft in the West. The SR-71 Blackbird was 92% titanium by weight. Even the F-15, designed for lower maximum speeds than the MiG-25, used titanium extensively in critical structures. Titanium offered the ideal combination of strength, low weight, and high temperature resistance. While American engineers were machining titanium on equipment that cost millions of dollars, Soviet mechanics were welding the MiG-25 together using techniques and tools you could find in any shipyard along the Volga. The engineers began measuring and weighing components. The numbers were shocking. The aircraft that Western planners assumed would weigh perhaps 45,000 pounds empty actually weighed nearly 64,000 pounds empty. That was heavier than some Western bombers. More than twice the empty weight of an F-15. How could such a heavy aircraft possibly achieve Mach 3 performance? The answer lay in brutal simplicity: raw thrust. The MiG-25 didn't achieve high speed through aerodynamic efficiency or lightweight construction. It achieved high speed by strapping two enormously powerful engines to a massively overbuilt airframe and accepting the weight penalty without apology. But as the analysis continued, engineers began to see method in what initially appeared to be madness. The steel construction, while heavy, had specific and significant advantages that became clear upon deeper examination. Steel was far cheaper than titanium, potentially by a factor of 10 or more. The Soviet Union could produce steel in vast quantities using existing metallurgical facilities across the country. Every Soviet industrial city had steel mills. Titanium, by contrast, required specialized processing facilities that existed in only a handful of locations, creating dangerous production bottlenecks and supply chain vulnerabilities. Think about what that meant for Soviet war planners. If enemy strikes hit those few titanium processing facilities, the entire production line stops. Every titanium aircraft in the pipeline grinds to a halt. Steel, you have 1,000 factories to fall back on. You have metallurgical capacity spread across 11 time zones. The Soviet Union had learned a brutal lesson during World War II, when the Germans swept deep into their territory and captured or destroyed critical industrial centers. The factories that survived were the ones that could be relocated, rebuilt, or operated from simpler facilities. Steel mills fit that profile perfectly. Titanium plants did not. This wasn't an oversight in the MiG-25's design. It was a direct reflection of how the Soviet Union thought about industrial survival under the most extreme conditions imaginable. Steel was also dramatically easier to weld and repair than titanium or aluminum. A damaged MiG-25 could be fixed at virtually any Soviet airbase using standard arc welding equipment and trained, though not specially qualified, technicians. Titanium repair required specialized facilities, inert gas welding equipment, and highly trained specialists. In wartime, when aircraft would be damaged and needed rapid return to service, or when operating from austere forward bases with minimal support infrastructure, the ability to repair your aircraft using the same equipment a rural factory uses was not a compromise. It was a strategic advantage. Soviet military doctrine emphasized sustainability and maintainability under combat conditions, not peacetime optimization. The welding itself revealed another layer of sophistication that initially looked like crudeness. American engineers looked at the MiG-25's welds and saw rough, thick, ugly seams. By Western standards, where flush riveting and smooth joins were both aesthetic and aerodynamic requirements. The MiG-25's construction looked like something assembled in a brickyard. But those welds were actually remarkably strong and carefully engineered for the specific thermal environment of sustained Mach 3 flight. Think about what rivets do in that environment. Each one creates a small discontinuity in the structure. At extreme speeds, different materials expand at different rates. Aluminum and titanium rivets would work loose or create stress concentrations as the structure cycled through temperature swings from -60 degrees Celsius to +300 degrees. You'd be flying a machine held together by thousands of tiny time bombs. The MiG-25's welded steel structure, by contrast, expanded and contracted as a single unified body. The welds were deliberately heavy to ensure they maintained integrity through hundreds of thermal cycles. Soviet engineers had tested this structure through exactly those cycles, from -62 +300, proving the welds held. The specific nickel-steel alloy used in the structure, designated VNS2 or VNS-4 in Soviet nomenclature, was carefully chosen for its properties across that wide temperature range. This alloy maintained its tensile strength at temperatures that would cause aluminum structures to soften and fail. It had excellent fatigue resistance under repeated thermal cycling. It had outstanding weldability using conventional arc welding techniques. And most importantly for Soviet industrial planning, it could be produced in massive quantities using existing steel mills without requiring a single new factory. American metallurgists examining the structure found that Soviet engineers had solved thermal expansion through clever structural design as well. The airframe had built-in expansion joints at strategic locations. Panels were designed to slide slightly relative to each other as the structure heated, then return to their original position when cooled. This prevented thermal stresses from building to dangerous levels. Western engineers working with lighter materials dealt with thermal management through exotic alloys and complex structural analysis. Soviet engineers simply overbuilt the structure to absorb the stresses, accepting the weight penalty in exchange for a solution that any competent welder on any Soviet base could understand, maintain, and repair. Then the teams examined the avionics bays, and the confusion deepened into what initially seemed like vindication of every stereotype about Soviet technological backwardness. Instead of transistorized systems with solid-state electronics, they found vacuum tubes. Hundreds upon hundreds of vacuum tubes. The radar system alone used over 600 individual tubes. The fire control computer used tubes. The communication systems used tubes. The instrumentation used tubes. 1976, vacuum tubes were technology from a previous era. American electronics had moved to transistors in the late 1950s and into integrated circuits in the 1960s. Western military aircraft used sophisticated solid-state systems. The MiG-25's avionics bay looked like something preserved from the 1940s. The CIA engineers who wrote the initial technical assessments were scathing. They began using the term steel pig in official documents. The nickname captured perfectly what seemed like crude, heavy, outdated Soviet engineering. Here was proof, they believed, of Soviet industrial backwardness. While American engineers were miniaturizing electronics and developing microprocessors, the Soviets were still using technology that had been obsolete for decades. The MiG-25 seemed like a dinosaur, a brute force solution to problems that Western engineers had solved elegantly years earlier. But as the analysis continued over the following weeks, as engineers tested the systems and understood their actual operating parameters, opinions began to shift dramatically. The vacuum tube electronics, while certainly older technology, had specific advantages in the harsh environment that a Mach 3 aircraft created. Advantages that no one in Washington had considered, because no one in Washington had ever needed to. First, and most critically for Soviet military planners, vacuum tubes were extraordinarily resistant to electromagnetic pulse. A nuclear weapon detonated at high altitude generates an intense EMP that can fry delicate semiconductor electronics. Transistors and early integrated circuits were highly vulnerable. Vacuum tubes were far more robust. In the nuclear war scenario that dominated both Soviet and American military planning, the ability to keep fighting after nuclear weapons had been used was not a theoretical concern. It was the central question. Imagine the scenario: nuclear detonations at altitude, EMP waves washing across the battlefield like invisible fire. Communications networks collapse. Radar installations across hundreds of miles go dark simultaneously. The F-15, with its sophisticated transistorized systems, goes dark too. Its radar dies. Its fire control fails. Its pilot is suddenly blind in the sky. The MiG-25, with its vacuum tubes, keeps flying, keeps scanning, keeps hunting. In the chaotic, radiation-soaked opening hours of a nuclear war, that aircraft remains functional while its Western counterparts are grounded by their own sophistication. That single difference could determine who controls the sky when it matters most. Second, vacuum tubes could operate at much higher temperatures than the transistors and early integrated circuits available when the MiG-25 was designed in the mid-1960s. At Mach 3, the aircraft's skin temperature reaches over 300 degrees Celsius in some areas. Inside the fuselage, temperatures could exceed 80 degrees even with insulation. The transistors of that era had temperature limits around 75 degrees. They required active cooling systems, adding weight and mechanical complexity to an aircraft already flying at the edge of what physics allowed. Vacuum tubes operated happily at temperatures exceeding 100 degrees. They needed nothing beyond basic airflow to keep functioning. Third, Vacuum tubes generated significant waste heat as a byproduct of their operation. Most applications, this was a disadvantage. In a high-altitude aircraft, it became an advantage. At 70,000 feet, ambient temperature drops to minus 60 degrees Celsius or colder. Electronic systems need heating to function at those temperatures. Solid-state systems require dedicated heating elements, consuming power and adding weight. The MiG-25's tube systems generated enough waste heat to keep the entire avionics bay at a workable temperature without a single additional heater. The inefficiency became efficiency in a different context. It was like discovering that a furnace you thought was wasting energy was actually keeping your entire house warm for free. Fourth tubes were far more readily available in Soviet industry than advanced transistors. The Soviet Union had massive tube production capacity from civilian radio and television manufacturing. Tubes were a known, mature technology that Soviet technicians understood thoroughly. Transistor production faced chronic quality control problems in Soviet factories. Using tubes meant using reliable, readily available components that could be replaced by any qualified technician at any base in the Soviet Union. Maintainability and logistics mattered more in Soviet military thinking than cutting-edge performance metrics measured in peacetime laboratories. The more American engineers examined the avionics systems, the more they recognized sophisticated system engineering hidden within apparently crude components. The radar, despite using tube technology, employed clever signal processing techniques. The fire control system, while not computerized in the Western sense, solved the necessary fire control equations reliably. The overall avionics architecture showed careful thought about reliability, redundancy, and real-world operational requirements. This wasn't ignorant backwardness. This was a conscious design choice based on different priorities and different industrial realities. The engines were perhaps the most impressive and revolutionary aspect of the entire aircraft. The Tumansky R-15B300 turbojets each produced over 24,700 pounds of thrust in full afterburner. These were not efficient engines by Western standards. They consumed fuel at what seemed like an astronomical rate to American engineers accustomed to thinking about range and endurance. A MiG-25 flying at maximum speed would burn through its entire fuel load in under 30 minutes. But these engines were optimized for exactly one operational requirement: getting a very heavy aircraft to Mach 2.8 and 70,000 feet altitude as quickly as physically possible, then sustaining that performance long enough to close to missile range and engage the target. For that specific job, they were magnificent. The compressor design was deliberately kept simple to allow reliable operation at the extreme inlet temperatures generated during high-speed flight. At Mach 3, ram air entering the engine inlets is compressed and heated to several hundred degrees Celsius before it even reaches the compressor stages. Standard turbofan or high bypass ratio engines would suffer compressor stall and flame out under these conditions. The R-15B300 used a simple axial compressor with relatively few stages, sacrificing efficiency for reliability and high temperature tolerance. The bypass ratio was 0. All incoming air went straight through the combustion chamber and turbine. This made the engine essentially a pure turbojet, terribly inefficient at subsonic speeds, but capable of operating reliably at sustained supersonic speeds where more sophisticated engines would fail catastrophically. What truly fascinated the American engineers was the inlet design and how it integrated with overall aircraft performance. At high Mach numbers, the positioning of the inlet spike became crucial. The MiG-25 had complex variable geometry inlet ramps that automatically adjusted position based on flight speed to manage the supersonic shockwaves entering the engine. When properly positioned, these shockwaves did much of the work of compressing incoming air. At maximum speed, the inlet shockwave compression actually contributed more total thrust than the engines themselves. The aircraft was essentially flying as a ramjet, with the turbine engines providing supplementary thrust and control. This meant the aircraft's maximum speed was limited not by engine power, but by the thermal limits of the structure and by how well the inlets managed those shockwaves. The official maximum speed was Mach 2.83, but Soviet pilots had stories of exceeding Mach 3 in emergencies. There was a reported case of a MiG-25 pursuing an SR-71 over the Middle East that briefly reached Mach 3.2. The aircraft survived, but the engines had to be replaced afterward due to overheating damage. This kind of emergency overspeed capability was deliberately baked into the design. If a pilot needed to catch an SR-71, if the mission was critical enough, the engines could be pushed beyond normal limits, with the understanding that they'd need replacement afterward. Compare that to the F-15's Pratt & Whitney F-100 engines, marvels of efficiency and power, providing excellent thrust-to-weight ratio, good fuel economy, and service life measured in thousands of hours. But an F-100 was complex, with variable geometry nozzles, sophisticated turbine blade cooling, and advanced materials throughout. It required specialized maintenance facilities and highly trained technicians. It cost millions to produce. R-15B300 cost a fraction of that amount, needed replacement every 150 flight hours, but could be swapped out in the field by a standard maintenance crew in under 4 hours using basic tools and a crane. The F-15 engine was built to last a career. MiG-25 engine was built to win a fight. Let me walk you through what this meant in practical terms. The MiG-25 had an operational radius of only about 400 miles when flying at high speed. Compare that to the F-15's 1,000-plus mile combat radius. But the MiG-25 wasn't designed for sustained air superiority patrols. It was designed to sit on alert at bases throughout the Soviet Union, scramble when an SR-71 or high-altitude reconnaissance drone appeared on radar, climb to intercept altitude in under 5 minutes, close to missile range, fire, and return to base. For that specific mission profile, fuel efficiency didn't matter. Raw performance did. And on raw performance at high altitude, the MiG-25 had no equal. The weapon system reflected the same philosophy. The MiG-25P interceptor variant carried 4 R-40 missiles. These were massive, nearly 15 feet long with 220-pound warheads. They came in infrared and radar homing variants, and the pilot typically carried 2 of each. The fire control system was relatively simple by Western standards. The RP-25 radar had limited look-down capability and could be jammed. But against a target at high altitude flying a predictable course, it was perfectly adequate. The radar's maximum detection range exceeded 100 kilometers. That was enough to find an SR-71 or B-70 and guide missiles to intercept range. The MiG-25 didn't need to be versatile. It needed to be deadly in one specific scenario, and it was. American intelligence quickly realized that the MiG-25 represented a fundamentally different engineering philosophy. Western aircraft design emphasized versatility. The F-15 was designed to dominate any air combat scenario, from low-altitude dogfights to high-altitude interceptions. It needed to operate from sophisticated NATO bases with full support facilities. Soviet design emphasized specialization and producibility. The MiG-25 did one thing extremely well. Could be manufactured in quantity using materials and techniques available across Soviet industry. It could operate from austere bases with minimal support equipment. Maintenance was simplified because the systems were robust, accessible, and repairable by standard crews with standard tools. The numbers tell the story. The Soviet Union produced approximately 1,300 MiG-25s in various versions between 1969 and 1984. They exported the aircraft to Algeria, Bulgaria, India, Iraq, Libya, and Syria. The total program cost was a fraction of equivalent Western programs. An F-15 in 1976 cost approximately $27 million per aircraft. Adjusted estimates suggest a MiG-25 cost perhaps one-third that amount. For a country that needed to defend 11 time zones of airspace against the most technologically advanced adversary on Earth, that cost differential mattered enormously. You can build 3 MiG-25s for every F-15. 3 intercept missions covered for the price of 1. The operational record is particularly revealing about true capabilities. In October 1973, during the Yom Kippur War, Egyptian MiG-25 Rupees conducted high-altitude reconnaissance flights over Israeli-held territory. Israeli F-4 Phantoms tried to intercept. They failed. The MiG-25s simply outran them. Israeli Mirage fighters fared no better. The Israelis fired missiles. The missiles couldn't reach the altitude where the MiG-25s were operating. Syria later deployed MiG-25s for similar reconnaissance missions. Between 1979 and 1982, Syrian MiG-25s flew dozens of missions over Lebanon and northern Israel. The Israelis, by then equipped with F-15s, managed to down a single Syrian MiG-25 in 1981. But that single kill required optimal conditions. The Israeli F-15 was already at high altitude. The MiG-25 was in a reconnaissance configuration with external fuel tanks creating drag, and the Syrian pilot made tactical errors. Under normal conditions, the MiG-25 could simply outrun any pursuer. Soviet use during the Cold War demonstrated the same point even more starkly. MiG-25 Rupees regularly penetrated Western airspace to test defenses and gather intelligence. They flew over Norway, over West Germany, and once buzzed a NATO exercise in the North Atlantic at Mach 2.8. NATO fighters scrambled every time. Every single time, the MiG-25s outran them. The interceptors couldn't catch them. The missiles couldn't reach them. The MiG-25s completed their passes, gathered their data, and flew home. This wasn't combat, but it was something almost as psychologically devastating for Western military planners. It was a demonstration, repeated again and again, that the aircraft fulfilled its design mission completely. It could go where Soviet commanders wanted it to go, and nothing in the Western arsenal could stop it. India operated MiG-25s quite effectively as well. During the 1999 Kargil conflict, Indian MiG-25s conducted reconnaissance missions over Pakistani-controlled territory at altitudes Pakistani defenses simply could not touch. Pakistani fighters scrambled but couldn't intercept. Pakistani surface-to-air missiles, including some of the most capable systems available at the time, couldn't reach the altitude where the MiG-25s were operating. India gathered crucial intelligence about Pakistani positions, artillery placements, and troop movements that directly informed Indian ground operations. The aircraft was roughly 40 years old at that point, its basic design unchanged since the 1960s, but it remained completely unchallenged in its element. Decades of technological progress in surface-to-air missiles and fighter aircraft hadn't closed the fundamental gap that the MiG-25 had opened in the 1960s. Speed and altitude, when pushed far enough, remained the ultimate refuge. Iraq used MiG-25s during the Iran-Iraq War. Iraqi pilots would conduct high-speed strikes, firing missiles at Iranian targets from standoff range before Iranian fighters could react. Iranian F-1 for Tomcats, among the most capable fighters of that era, managed to shoot down several Iraqi MiG-25s, but only under optimal conditions, and usually during takeoff or landing phases, when the MiG-25 was slow and vulnerable. In level flight at altitude, the MiG-25 could outrun anything Iran possessed. The fuel system exemplified Soviet pragmatism at its sharpest. The MiG-25 used a special fuel called T6, essentially high-purity kerosene with additives to improve thermal stability. At high speeds, standard jet fuel would break down from the heat generated by aerodynamic friction. T6 could withstand those temperatures, but it wasn't compatible with standard jet fuel. A MiG-25 couldn't refuel from conventional tankers or at standard airfields. This limited operational flexibility significantly. Soviet planners accepted that limitation without hesitation because forward bases where MiG-25s deployed would stock T6 specifically for these aircraft. The specialized fuel was part of the specialized mission. You don't ask a scalpel to also be a hammer. The development cycle itself is worth examining side by side. The Americans spent 12 years developing the F-15, incorporating lessons from Vietnam, feedback from operational pilots, and cutting-edge technology at every stage. The result was a magnificent aircraft, arguably the greatest air superiority fighter ever built, but that development took time and cost enormous sums. The MiG-25 went from design initiation to operational service in 7 years. Soviet engineers didn't try to create a perfect multi-role fighter. They identified a specific threat, designed an aircraft to counter that threat, and got it into production using available technology and materials. 12 years and billions of dollars versus 7 years and a fraction of the cost. The Americans built the perfect fighter. The Soviets built the right one. When Western engineers finished analyzing the MiG-25, they had to reassess their assumptions about Soviet capabilities fundamentally. Yes, Soviet technology lagged behind Western technology in many areas: metallurgy, electronics, precision manufacturing, but Soviet engineers excelled at solving specific problems with available resources. They weren't trying to match Western technology component by component. They were finding different solutions that achieved the same necessary results. The Steel Pig nickname gradually disappeared from official documents. In its place, came more nuanced assessments. The MiG-25 was recognized as a brilliant piece of specialized engineering. It wasn't the superfighter Western intelligence had feared. It couldn't dogfight. It had limited situational awareness. The radar had significant limitations in certain scenarios, but within its design parameters, it was formidably effective, and it had been produced in numbers that would have been economically impossible using Western design approaches. Let's consider the strategic implications. The B-70 Valkyrie program was canceled in 1969. Only 2 prototypes were ever built. The official reason was cost, but the existence of the MiG-25 played a significant role in the decision. If Soviet interceptors could reach Mach 3 and operate at 70,000 feet, the B-70 survivability was questionable. Invest billions in a bomber that might be vulnerable. The SR-71 remained in service, but it never flew over Soviet territory. The Soviets made clear that MiG-25s would intercept any aircraft that violated their airspace. American planners believed them. This created a fascinating strategic dynamic. The MiG-25 essentially deterred certain American capabilities without ever firing a shot in anger. The mere existence of a credible high-speed, high-altitude interceptor forced the United States to abandon high-altitude penetration bombing entirely. Strategic reconnaissance over Soviet territory was abandoned. The entire doctrine of projecting air power into the Soviet heartland through speed and altitude alone was scrapped. American military aviation shifted toward low-altitude penetration, terrain-following flight, and eventually stealth technology approaches that relied on hiding rather than outrunning. These were areas where the MiG-25's specialized design offered no advantages whatsoever. The Steel Pig had reshaped American strategic doctrine without ever leaving Soviet airspace in anger. It didn't need to shoot anything down. It just needed to exist convincingly enough that American planners changed their plans. The technology transfer from examining Belenko's aircraft influenced Western design as well. American engineers saw how the Soviets solved high-temperature welding problems in steel. They saw how robust vacuum tube systems could be in harsh environments. They saw elegant solutions to inlet design problems for high-speed flight. Some of these solutions influenced later American designs, though modified to fit Western manufacturing capabilities and design philosophies. The student learned something from the teacher, even when the teacher appeared to be behind. The reconnaissance variant, the MiG-25R, deserves special attention. It carried sophisticated cameras and sensors in a ventral bay. The camera systems were actually quite advanced, using long focal length lenses that could capture high-resolution imagery from extreme altitude. Some variants included side-looking airborne radar for mapping and reconnaissance. The combination of high-speed, high-altitude, and capable sensors made the MiG-25R an excellent reconnaissance platform. Soviet pilots would cross borders at Mach 2.8, make a single high-speed pass, and exit before defenses could react. Film would be developed and analyzed within hours. Speed was the stealth. By the time anyone knew you were there, you were already gone. Now let me share what I think this story ultimately reveals. The West fell into a trap of assuming that superior individual technology automatically translates to superior military capability. The MiG-25 proved that assumption false. Soviet engineers understood their industrial base, their operational requirements, and their strategic context. They designed accordingly. The result was an aircraft that achieved its mission objectives using technology Western engineers had dismissed as obsolete. This has profound implications for how we think about military technological competition today. China currently faces challenges remarkably similar to those the Soviet Union faced in the 1960s. Chinese technology lags behind American technology in many areas, but Chinese engineers don't need to match American capabilities component by component. They need to develop systems that achieve their strategic objectives. If China developed an aircraft today using simpler materials, more robust electronics, and specialized design for specific missions, Western intelligence might initially dismiss it. The MiG-25 suggests that would be a serious mistake. The economic factor cannot be ignored either. The Soviet Union spent perhaps a third of what the United States spent on comparable capabilities, accepted trade-offs in versatility and sophistication to gain advantages in cost and producibility. For nations with smaller defense budgets, this model remains deeply relevant. An air force that cannot afford 250 advanced multi-role fighters might be able to afford 500 specialized interceptors. Those 500 interceptors, properly designed for their specific mission, might provide more effective defense than a smaller number of more sophisticated aircraft ever could. Looking at modern threats, the principles embodied in the MiG-25 continue to echo. Hypersonic weapons are essentially MiG-25 philosophy applied to missiles. Go very fast in a predictable trajectory, relying on speed alone for survival. Anti-access area denial systems often prioritize robust, numerous capabilities over sophisticated, expensive ones. The concept of specialized platforms optimized for specific missions rather than multi-role versatility continues in both Chinese and Russian military development today. Before we wrap up, if this deep dive into Cold War engineering and military strategy is the kind of content you want to see more of, hit that like button and subscribe to the channel. Your support is what makes these in-depth analyses possible, and your engagement helps bring this content to more people who appreciate the technical and historical detail. American engineers stopped calling it the steel pig once they understood what they were looking at. They saw an aircraft that flew faster than an SR-71 in level flight. They saw an aircraft that could be produced in numbers sufficient to defend the largest country on Earth. They saw an aircraft that enforced fundamental changes in Western strategy without ever firing a shot. Most importantly, they saw that their assumptions about the relationship between technological sophistication and military effectiveness were incomplete. The Soviet Union lost the Cold War for many reasons. But it wasn't because the MiG-25 was a bad aircraft. The MiG-25 was exactly what it needed to be. Viktor Belenko's Defection gave Western intelligence an unprecedented look inside Soviet military aviation. But the real intelligence value wasn't in discovering that Soviet technology was crude. It was in discovering that technology properly applied to the right problems within the constraints of a specific industrial reality could be devastatingly effective regardless of how it looked on paper. That lesson, learned in a hangar in northern Japan in September 1976, continues to resonate nearly 50 years later. The steel pig delivered. Welded steel structure, vacuum tubes, and all.